Thanks for the introduction, and thanks for everyone to come to my presentation. And the title is Edge-based balloon icono-active contours for image segmentation. And I'm Dan Chen, and this is a joint work with Professor Laurent Cohen and Romain Mirbeau. Actually, firstly, we show the main goal of this work. You see, there is a picture, and we want to extract the boundary of this object by these three control points. And here is the goal, and we want to find a closed contour passed by all these 3 points, and then to find the complete closed contour of this object. So here, our tool is to use the deformable models. The classical deformable models can be carried out by the co-evolution scheme, and the contour will move to the boundary in terms of scalar valued speed function in its normal directions. And in this picture, and the black arrows indicate the normal directions of the active contours. And here is the intermeter result, and finally it will converge at the real boundary of this object. And here we show some disadvantages of this co-evolution scheme. Firstly, it's very difficult to take into account the fixed points. And the second is that it is sensitive to local minima. And finally, it costs a very high computational complexity. But a very good advantage of this model is that it can get a closed simple curve. And an alternative method for the deformable model is the minimal path method. This minimal path method aims to find the globally minimizing curve to minimize this curve length. And in this formula, f is the geodesic metric. It is a positive function, and it is convex and one homogeneous on its second argument. And here is a picture. And here, using the provided points, and then we can get a minimal path between the 2 points. Okay, so this method, the advantages of this model is that we can get the global optimality, and there is a theory of numerical solutions. Tools is very fast and efficient, but this for this model it's difficult to find a closed contour. This is a good model to find an open curve, but okay, we show an example. First, we see again this picture. There are 3 using provided points, and we want to find the closed contour passed by the 3 points. Okay, so firstly we extract the minimal path between the point P1 and P2 is okay, and then we extract the path between P2 and P3. And however, when we extract the path between P3 to P1, we see the overlapping. This path will overlap the previous 2 geodesics. Our goal is to find a path go this way, and then to form a closed contour with the 2 previous passes. Okay, so a possible solution provided in this work is to combine both minimal path models and the co-evolution scheme. Actually, we need the new model to have the 2 properties. Firstly, during the co-evolution, we need the 2 successive contours to be close to each other. This means that gamma t is close to gamma t minus 1, and we also require that at any time the closed contour gamma should comprise our set of minimal paths. Here we illustrate this idea. First, we see 3 points here, and we see 3 points. With 3 points, this set of points are provided by Usner, and we evolute these geodesics, and finally we can find the contour that pass by the 3 points. Okay, so now there are 2 problems should be solved in this new scheme. The first problem is that how to ensure the 2 successive contours to be close to each other. So now we firstly solve this problem. In this picture, we see an initial contour, and there are also 3 user provided fixed points, P1 to P3. And we first decomposed the initial contour into 3 subpasses. These passes link each pair of successive points. And then we build a tubular structure neighborhood for each subpass. Okay, and then we extract the geodesic between each pair of points within this tubular neighborhood. Okay, and we finally do this. And then we can see a new closure contour can be obtained. Another key point for our method is how to design a suitable geodesic metric so that when the initial contour are far from the target or boundary, the active contour will move towards the target edges. So here we use the balloon force. In this energy function, we have 2 terms. The first term is geodesic covariance. It invokes a positive definite symmetric tensor field M and a balloon force term. This is a region-based term. Our goal is to transfer this balloon force into a line energy. So here I gamma means the interior region of inside the path gamma, and M is a tensor field. It can be constructed by its eigenvalues and the eigenvector. The eigenvector is V1 and V2. V1 is collinear to the edge directions, and V2 is orthogonal to V1. And how is the edge, the norm of the edge gradient? It indicates the image edges, and here V2 is collinear to image gradient. Okay, so we see how to transfer the balloon term into a line energy. Okay, in this equation we use the divergence theorem, and then we can get a line energy here, and then we rotate each component in anti-clockwise order, and then we can get this line energy. And here the vector field V is actually obtained by this divergence equation. Okay, so now we can show how to design a suitable metric. This is the balloon edge-based energy, and by the previous formulation, we can get a geodesic co-energy. This involves a random metric, and it includes 2 parts. The first part is a symmetric part, and second part is a linear and asymmetric part. And here is the tensor field is constructed like previously, and then we, in order to ensure that this metric is positive everywhere, we need to rescue the norm of the vector field omega by this nonlinear mapping. Okay, so we introduced the render iconal PDE. Firstly, this is the this is the render metric, and it should be positive everywhere. And then we need this inequality to be held. And here is the geodesic distance map associated to this render metric. And this is the iconal PDE. We can solve this iconal PDE by the fast machine algorithm. Okay, actually, in this picture, we show the course of the minimum path evolution in a real image. So in this picture, we use scale 5 points in a clockwise order. And here is the edge salience map is obtained by the image gradient norm. Okay, so here is the first step. We can see the path will move towards the boundary. And here is the second step and third step, and finally we can find the converged boundary. Okay, so here's some segmentation result compared to the geodesic active contours. Okay, in the first column we show the initial contour and the fixed points, and here the second column shows the image gradient map, and the third column are the geodesic active contour result, and finally is our result. We see in the third column some part of the contour has leaked into the background, but some part of the contours have not reached the boundary. But with the fixed point, our model can get the good segmentation result, even in some very weak edges here like this. Yeah. Okay, thank you.
So we have time for questions.
Thank you for your presentation. Have you evaluated the complexity of your algorithm?
Actually, the computation of complexity means the computation of the geodesic methods and the vector field data, computation of the vector field data. But these computations are fixed inside the tubular structure, so it's very fast. So the tubular structure is only a small detail.
You program it in MATLAB, in C++, or what?
The real computation is carried out in C++.
Plus. How long is it for C++ language program? In this application, how long is it in CPU time? Okay, thank you.
Did you compare the results with, for example, some usual and old algorithms such as intelligent skissers?
Small practical question about when you introduce the metric. Can you show us the slide M? Next one. Oh, sorry. Next one. This M. So where is a closed bracket? I think it's first exponent. So I think one bracket is missed. Yeah. I should it. I think it's. Can you show it again? M. Yeah. The previous slide.
This one?
No. Next one. Yes, exponential, yes. Yeah. So can you tell me where is the closed bracket? That's my question. Can you check the brackets? The closed bracket, one more. Where should I close the bracket? Yeah, in M expression. It's just very formal question, but I want to understand how to write M correctly. Where should I close the bracket? There is one more bracket that is open but not closed. It's product of exponential in this sum, yes?
Yeah.
Here.
Oh, yeah,
Here. Okay. That was my just now I understood. Thank you. Yes. Yeah, I thought about this, but just to be sure, now I see it. Thank you.